I will talk about ordinary differential equations with random initial data, and this is an interesting subject because it puts together concepts from ordinary differential equation, probability, and also PDEs. Suppose that we have an ordinary differential equation, x of t, taking values in Rd, is going to be our solution, and x satisfies this ODE, x of t, so the derivative in time of x is equal to g of x, where g is some function. And I'm going to assume that g is regular enough so that when I start from some initial data, x0 in Rd, I have existence and uniqueness of solutions. Now the question is, suppose that actually I don't know exactly the initial data. The only thing I know is something about this initial data, and is that it follows some law that I call f0. So x0 is a random variable, and that implies that x of t, that I will denote by this little xt, is also a random variable, so it's going to follow a law that I call f of t. The question is, what is this f of t? What is the law of xt? And we can consider two very simple examples. The first one is assume that g is exactly 0, so our ODE doesn't change. For every time t, the value of the ODE is simply x0, and that means that the law of xt is going to be f0. Another simple example is to consider a very simple initial data, where x0 is equal to 0 with probability 1/2, or is equal to 1 with probability 1/2. And then x of t is going to be the solution of our ODE starting at 0. Here, this is what I denote by x tilde of x0. So the solution of my ODE starting at 0 with probability 1/2, and the solution of my ODE starting at 1, which I denote by x tilde x1, with probability 1/2. So this gives me the law of my x of t. Now I want to look at the general case. So this case here. You give me any law initially, and I want to know what is going to be f of t. And what we are going to see is that f of t satisfies a partial differential equation. I copied here again the ODE that we are working on, and I can write this in integral form. So I simply integrate over time, and I have this shape here, and this I do it just for convenience because I don't want to deal with derivative in time. Now the question is, I have my x, how I make the law appear, how do I relate x with its law? And there is a very simple and straightforward way of doing this. If you have x, some random variable that has a law f, we consider any function f with some regularity, say continuous and bounded, and we compute the expectation of f at the random variable x. And this, by definition, is the integral of f against the law f. And this is a very simple way of relating the random variable x with its law f. Notice just here that I put little y to stress that this is the integration variable. With this, we can apply this result to our ordinary differential equation. Now I take f, a function that is applied to x. F, say, is a function that goes from Rd to R, and I'm going to consider that this is what we call a test function, meaning that it's say infinity, so it's infinitely differentiable, and it has compact support. And I differentiate over time this function f evaluated in the solution of my ODE, so evaluated x of t. And what do I have? Okay, I just differentiate. I will have the gradient of f with respect to its variable x applied to x of t, inner product with x dot, the derivative in time of x. And then I know what x dot is. X dot is precisely the function g here. And now I'm going to compute the integral form. I simply integrate over time, and what I obtain is that f of xt is equal to f of x0 plus the integral between 0 and t of this term here now integrating with respect to the variable s. And this is what I'm going to work on. Now I have my function f, right? So as I had here, and simply what I'm going to do is compute the expectations. And I remind you that the expectation is a linear function. So what I'm going to have is I'm going to apply the expectation to each one of the terms. I'm going to write the definition of the expectation. This expectation here, because my random variable is x of t, is the integral of f against the law of xt, and the law of xt is precisely what we denoted by ft. When I compute this expectation, this is going to be the integral of capital F against the law of the random variable x0, and the law of the random variable x0 is what we denoted by f0. And now here I have to do a small thing. First of all, I put this integral inside, so the expectation I can put it inside. And now what I have is these random variables. It's again a different function. It's not f, but it's the same idea. I have the expectation of this function here. This is going to be the integral of this function against the law of xs, and the law of xs is precisely fs. So now I have this expression above written in terms of integrals. So I have made the law ft, f0, fs appear. And now simply what I can do is to put all the terms together. I factor out the f, because these can be interpreted as a PDE for ft for the law in weak form. Okay, and what does it mean? What is the PDE here? First of all, we are going to factor out f, as I said. So we have f of t and f0. This is easy. We just put f0 on the other side of the equation. Here, because we want to factor f, we need to do integration by parts. Because of integration by part, this gives us a divergence. Notice that in this integration by part, we are not going to worry about the boundary terms, because I'm assuming that f has compact support, so the boundary terms disappears. And I just have this expression here, and this is supposed to hold true for all f test functions, so I remind you that it's infinitely differentiable and with compact support. This implies in particular that I'm going to have this integral expression almost everywhere. If f is also differentiable in time, then I can differentiate this expression here, and what I obtain is precisely my partial differential equation. F, the law of xt, satisfies that the changes over time follows minus the divergence in x of the product gf. And this is my initial data. So just a final recap, we started with this ODE here, where we say the initial data is actually random. It follows a law f0. And the question was, then xt is a random variable, what satisfies the law of this random variable? And this law is what we denoted by ft. And what we saw is that what we obtain is a partial differential equation for f of this form here. So g appears in this divergence term. And the key thing here to obtain the equation for f was to compute the expectation of this random variable when evaluated against some particular function. That's all. Thank you.